All right, here we go. Welcome to lesson 11.5, geometry notes, volumes here of prisms, cylinders, and pyramids. So we'll look at, it's kind of switching gears a little bit here as far as we'll talk some volume of these geometric solids that we talked about in the last lesson, um, and basically how to find that volume. So let's start there. What is volume? We don't need a big fancy definition. I'm kind of counting on us to have an idea of what this is. Let's just say the amount of space. We could say cubic, to be a little bit more technical, cubic units. And here's where we get a little bit loose, inside or contained within a geometric solid. Oops, solid. That's not right. Oh, a geometric solid. So yeah, how many cubic units could you fit inside something? And then with same deal, without going super fancy on this Cavaliere's principle, it's what's being illustrated right here, that it basically says that if the area of the base, okay, stays, is the same. So let's say this purple area here of this two-dimensional, what looks to be maybe a square, a quadrilateral at least, that area is the exact same area as this. It's a different shape, but the height of these two prisms is the same. It doesn't matter if it's tilted like this or what we would call straight up and down. So this is what we would call oblique, and this is what we would call right, is what they're kind of meant to be illustrating here. If the heights are the same, the distance from the bottom base to the top base are the same, the volumes would be the same. So that's what Cavaliere's principle. We just jotted that down as far as that's what that's called. It's really just going to allow us to use the formulas. This is really what we wrote. It's going to allow us to use the formulas, whether our shapes are right, or it's kind of like that straight up and down, or oblique, which is kind of this slanted, this tilted version. Okay. All right. So that's a little bit of the vocab of just kind of what we're going with here today. Let's just get the formulas knocked out. They're on our formula sheet. They're not things you have to memorize. So the volume of a prism is fairly, like, it looks pretty benign, like just two things, capital BH. Now that's a loaded capital B right there. It stands for the area of the base, and then the height is the distance between the bases. So you're seeing that same illustration here. That height is that distance between the bases, but this could potentially be, like, this capital B could be a lot of different things, right? Just to look at a few of them, our bases could be triangles. Well, now that capital B turns into 1/2 base times height. It could be even just quadrilaterals have a lot of different formulas. It could be a trapezoid. Well, that's 1/2. Well, let's do it. Why not? If my base, if this is a trapezoidal prism, something like that, well, I'm going to have to find the area of the base. That's a totally different formula. 1/2 base 1 plus base 2. I'd actually have to look, times the height, the distance between those bases. So there's another example. What if my base was, could be a rectangle, could be a hexagon, or another regular polygon? Well, now all of a sudden that B becomes 1/2 apothem perimeter. And I'm just kind of grabbing, I'm just trying to illustrate that depending on what the base is, we could have a multitude of different formulas that go in there. Okay, so just be aware that it looks kind of simple, but it's more than just two numbers being multiplied. In some cases, you might have to find, Pythagorean theorem to find a missing side length, base and height, stuff like that. Trigonometry to find your apothem. So there's volume of a prism. Area of the base times the height. Cylinder is actually the same, because what's a cylinder compared to a prism? It's exactly the same thing, except our base is always a circle, right? That's the big difference. Here, the base could be a square, rectangle, triangle, hexagon, whereas with a cylinder, the base is never anything but a circle. So because that's true, instead of going, capital B times H, area of the base times height, we know what the area of the base always is. It's pi r squared, right? The area of a circle formula. So this one's a little bit nicer in that there's not all those options that we were just kind of going through. There's just one, pi r squared times height. So we'll work with this one exclusively. Why would I ever look at that when I say, hey, I need the radius, I need the height in our formula? So cylinder is a little bit more straightforward. R is our radius. I mentioned that. And then kind of in the same breath here, well, like I said, let's get our formulas kind of knocked out. The volume of a pyramid, and again, whether it's what we would call a right pyramid or oblique, still applies those same concepts. Um, it's just like our prism one, BH, right? I got the BH, except 1/3. So you could think of it as a prism with this exact same base would just be B times H, and we got if it's a pyramid though with that same base, we'd have 1/3 of the volume there. So we have the same issue though. Our base could be a square, it could be a rectangle, it could be a hexagon, could be a triangle. So our pyramids could have any base that we have a formula for. So that's what we'll be working with. So let's do them. I mean, for the most part, that's kind of the notes. Was those 3 formulas. We'll do one more here at the end, just kind of a shorter one. But it's more just kind of practicing and using the formulas. It's not. It's well. Let's do them. Let's talk through them. There's some easy ones. There's some hard ones. So I got a couple different 1A, 1B, 1C examples. Just here we go. Find the volume of it. So you pause it, you try it, you set it up. Here's the solution. So when I look at it now, be careful here that we say, hey, what is? We know. I think this kind of starts with what kind of solid is this? It's a triangular prism. So I grab my generic formula, for area of a prism, area of the base times height. But then the question, and the reason I have this one on here is sometimes people get messed up. The base is not necessarily the bottom of the figure. The base is not this rectangle down here. What? The base is the triangle. We said it was a triangular prism. So this, as the front, as we kind of look at it, that's actually the base. So when I go to, here's how I always do these. I basically replace my capital B with the formula that I'm going to use. Whoops, that's 1/2 base times height. That's how you find the area of this triangle, because that's the base. And then the second H now, the height, remember, is the height of the prism, which is the distance between the bases. So I think I have everything I need as far as getting them into our formula here. And because it's all multiplication, there's no reason that we don't need the parentheses. I just kind of show that because that's what B became. So the 1/2 is great. I'm going to use this for the base of my triangle. I'm just looking at this as like a 2-dimensional triangle base, 5 and 8. That's perfect. That's exactly what we need. So the base we can call 5. The height we can call 8. 1/2 base times height. And then the second H, the height of the prism, is 3. So awesome. That works out great. So that's an example. As long as I can identify the base, I have everything I need. And we crunch it. Let's see. Can we do it without a calculator? 8 times 5 is 40. Cut that in half, 20. 20 times 3 is 60. Oh, no. I'm second guessing myself. 60 cubic centimeters. Yeah, there we go. We're good. Okay, so not bad. There's a prism example. And we can only hit so many here in our notes. So that's our prism example. But we could have rectangular prisms. We'll see some other ones too. Keep her moving. Find the volume of what is this? A cylinder. All right, we'll take that one. Cylinders, like we said before, just because of the nature of the formula, right? We said the formula was this area of the base, but the base is always pi r squared times the height. Because of the nature and that always being the same with the cylinder, these just tend to be a little bit easier. So hopefully we can do it. We got the pi, love it, got it. R, do we have our radius? Sure, 4. Okay, so 4 squared. And then the height, the distance between the bases, we have as well. So it's another one. There's 2 in a row here that it's like, sweet, we'll take that. Grab the calculator, see 16. I'm doing the 4 squared is 16 times 7. So you could go exact on one like this and say 112 pi. I'm just going to crunch the pi right away and say this is about 351.86 cubic centimeters. So we'll take those ones. Those ones are nice. Gets everything where they're supposed to go. There's our cylinder example. Let's do one more. Okay, well, we'll do a few more, but one more just straight up kind of find the volume of the solid. So it's our third one that we talked about, our pyramid. So if I look here, just getting the generic formula, volume equals 1/3 area of the base times the height. So let's customize that a little bit. The 1/3, that stays put. What's my base shape here? My base, oh no, it's a hexagon, regular hexagon. So that one we had a formula for, which was, let's see, probably need a little more space here. 1/2 times apothem times perimeter. Okay, that's how you find the area of a regular hexagon. And then the h, again, the second h here is going to be the height of the pyramid in this case. So let's see what we got. We have a lot of it, I think, right? So as far as information go, I've got the 1/3, all good. The 1/2, just like our triangle one, which is a constant. I don't think I have the apothem. Let's look here. So if I just kind of like before, go two-dimensional with my base and say, all right, that's a regular hexagon. I know this is 12. We need that length right there. That's my apothem length, right? But because the 12 is a side length and there's 6 total sides, 6 times 12 is 72. So I think perimeter-wise, perimeter we need, we can use that, 72. And then actually this last h as well, the height of the pyramid is 20. So here's what I like to do, like I said, is kind of lay it all out and just see what do I need here? Can I crunch this right now? I say, no, not quite. I don't have all the numbers. I need to figure out what that apothem is. And once I have it, I'm going boom, times 1/2, times 1/3, times 72, times 20. But this one's potentially a little work, right? So if I draw my couple radii in there and say, all right, let's figure out what the central angle is. If you're wondering what's going on here, go back and check 11.3 notes. I'm going to go a little bit quicker here. There should be something it's a concept that we covered in a previous lesson. So how do I find that? 360 divided by 6. So this combined angle up here is 60 degrees. We only really need to work with one of those angles. So we're going to use 30 right there. Okay, I'm redrawing, I guess, this triangle right here a little bit bigger. The common mistake, make sure you're not using 12. 12 is the full side length. We're cutting a couple things in half. The central angle gets cut in half to 60, and then the side length, 12, got cut in half to 6. So that's kind of the information we have right now. We can find A. I'm actually, for setup-wise, for ease of solving, I would just personally probably go work with this angle right here, which has to be 60. Because if I stand right here and label my sides opposite and the one right next to me adjacent, I end up with just a slightly shorter solve. So the tangent, right? Tangent is opposite over adjacent. Tangent of 60 degrees is opposite over adjacent. And we said the reason I'm standing at the 60 is now if I go 1 times A, I get A, which is equals to 6 times the tangent of 60, which when this is all said and done is about what? Whoops, I don't want to go too far there. 6 times tangent of 60. So we're getting about 10.3923, but it's continuous. I like my answer. I think that makes sense as far as that's about what I would, 10-ish. If this is 12, okay, or if this is 6, this is going to be larger. That's fine. Just keep it on your calculator because now that, like we said, from the game plan, that was the last thing we needed. That's going in right here. I'm not clearing. I can just keep it on there and go, let's start on the right. Times 20. So times 20. Times 72. Don't have to push equals. Times 0.5 or 1/2. And then you could either go divided by 3, right? Times 1/3 is the same thing as divided by 3, or use the fraction function on your calculator and just type it in as times 1/3. When it's all said and done, crunch, 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 calculator's spitting it out. My final volume of this particular pyramid, 2,494.15 cubic centimeters. don't let the size, of the number be like a deterrent. We're throwing a third dimension in there. So you're multiplying some big numbers. 72 times 20 by itself is a big number. That gets multiplied by 10. Now we cut it in half times 1/3, but still, that we're going to see some bigger numbers with volume. All right, so there we go. Hopefully you're able to get there. A little trigonometry. Didn't have to use trig. You can use model right triangles as well. This is a 30, 60, 90 triangle, so there's some other options as well. All right, let's keep moving. There's not a new note. Let's just look at an example of maybe using the formulas in a different capacity here. So now it's telling us, hey, you've got the volume of the cylinder. It's 1,253 cubic centimeters. Find in this case, what we would call the radius. So great, fine, awesome. We've got our formula. I always start the same way. Volume equals generic pi r squared times h. And then it's a matter of let's fill in what we know. So we know 1253 is the volume. Pi is a constant. We don't know r. If you want, you could put x in there. Why don't we do it? X squared. But we do know the height of the cylinder is 10. Okay. Yeah, how are we going to do this? Let's move everything away, I guess, from the x. You can do it in one kind of felled swoop here, as long as you keep track of your division, your order of operations, maybe put parentheses around that when you're dividing it out. So pi's would cancel, tens would cancel. So I know you can't see me, but on my calculator, I'm doing 1253. I usually just push divided by 10, push equals, and then divide by pi. So my calculator is saying about 39.8842 ... continuous, and that's equal to x squared. So we're not done, but if we're trying to stay accurate, I don't clear my calculator, and I know that, hey, just to finish this, I'm going to need to square root both sides here to undo the x squared. So x ends up being, drum roll, second square root, second answer. I'm going to stick my last answer in there. About 6 point, if I round it, 32 centimeters. A lot of centimeters today. It was 6.31539, but if I round to the nearest hundredth, it'd be 6.32. All right. So again, we could do that with a pyramid or a prism. This one just happened to look at a cylinder. So using the formulas just in a different way to find a missing dimension, a height, a radius, maybe a side length on a base, something like that, an apothem, maybe apothem. Okay, awesome. One more look here. Okay, we're doing okay. It's not overly, hopefully not too bad. Find the volume of the solid. So now this is one, when I look at it, just says find the volume. First off, just what's going on here? We've got the overall big shape. This would be a triangular prism. But then there's been this, it's like a hole punched out of it. There's looks like to be a square prism that's been removed. So this inner would be like hollow here. You could stick your arm through the middle of that. Be a long arm because it's 6 feet from the front to the back, but you could lay down in there. Anyways, so same deal. I would do a game plan for this where I say, all right, well, how are we going to do this? I'm going to find the volume of the triangular prism, figure out what that is, and then we would just let's just subtract off the volume of the square prism. Yeah, we can do that. So it's like two problems in one, basically. How do you find the volume of a prism? It's we'll just go to the formulas. Area of the base times height. Area of the base times height. Great, awesome. Because our base is this triangle, our B becomes 1/2 base times height, and then this second H, remember, is the height of the prism, which I know it's 6. That's awesome. For the square, well, why not? The area of a square is side times side, or side squared, and then we'll multiply that by height. So again, it's kind of just having a game plan. What do we got here? So now one of these is easier than the other. I kind of wrote over the top. I don't want to lose any of these markings here. I'm actually going to start with the volume of the square prism, because if I look, I see that each of these sides here are 3. That's what the arrows point to, that the side lengths are 3. So that's kind of nice. 3 side length squared. That's how you would find the area of the base. and then the height of this prism that's been removed is the same height as the height of the triangular prism. So that's one that I have everything I need, 3 squared, and then times 6, everything's where they're supposed to go, or we have all that information. Okay, the triangle's a little tougher, actually. This is just like the other couple ones we did. I would draw this two-dimensionally and just see, okay, hey, it looks to be, and it is, I can tell by the markings, and a different set of markings here, that we have double tick marks here, 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 and here. So this is an equilateral triangle. I know this edge is 10, but that's it. Oh my goodness. How do I find the area that I can't just go 1/2 times 10 times what? We got to figure out what the height is. So what I would look to do, I don't think we have to use trigonometry. You could. These are all 60, right? And an equilateral is equiangular. So you could do stuff with the 60 degrees, split it. This is ultimately the number we're looking for, is what is that height right there? Because I could go 1/2 times base times whatever our height is going to be. We don't know. We'll leave a little blank for it. And then the height of the prism, which is still 6. Right? This whole thing hinges on us on finding whatever this h is right here. All right, and once I got it, boom, there it goes. And then we'll subtract off this number over here. So how do we do it? I would use Pythagorean theorem. I'm going to use Pythagorean theorem, right? Because, well, what do you mean? How do you use Pythagorean theorem? If this is 10 and it's equilateral, this has to be 10, this has to be 10. So I could split this apart and look at this as a hypotenuse of 10. We're looking for the h. I'm kind of looking at this triangle right here. It's a right angle right there. Just making sure that I use 5, very similar to the one that we did earlier, for the side length. This one's just nicer because we have the hypotenuse length. So in the end, I'm crunching h squared. I'm trying to leave a little space here. H squared plus 5 squared equals 10 squared. So 10 squared is 100, 5 squared is 25, so 100 minus 25 is 75. So I'm just trying to save a little space here. So the height, when it's all said and done, is once I square root 75, that's our h. Now it's not exact, and it is what it is. I mean, we could look at it. The square root of 75 should be it's 8.66 continuous. But because I know what's going on and I kind of made a model for myself, there I go. I'm going to plug that in right now. Maybe I do this 3 squared, which is 9. 9 times 6. This is 54, so that's kind of a nice clean number. So in the end, let's not forget to subtract 54. But here I go. I've got that square root of 75 on my calculator. I'm going to go times 6. So times this 6 times 10. And then times 1/2 or 0.5. So the area of the triangular prism, if you're just kind of getting a number and you want to make sure you entered that correctly, is about 259,807 continuous. Okay. And I know I'm getting kind of cluttered here, but we're almost done. Just don't forget to do this now. Subtract off the 54 minus 54. Oh, there we go. So the overall volume equals 205. That's what I got. 0.81 cubic feet. So there we go. I would say that's pretty common in that, most of the time we have the information. There's only so many ways that we kind of find missing information. What are they? Pythagorean theorem, really common. Maybe some trigonometry, still pretty common. That's about it, right? Like there's not a whole lot of ways to come up with information on our own. So most of the time this is a perfect example. We knew everything except one number. A little bit of work, found it, and then it's just that organizational piece of having something to having a plan to do with it what we're supposed to do. So, all right, back to the notebook just for a quick note here on similar solids. We'll look at an example, and that's that. So here we go. Similar solids. What does it mean? We've talked similarity quite a bit actually in this course. And hopefully it's exactly what you would think would be, that two solids are similar. if their corresponding linear measurements have the same ratio. Okay, so like the height of one prism is proportionate to the height of another prism, and then the side length of that first prism has the exact same ratio to this side length, or a pyramid has the same um, base edge ratio as their heights do. So it's that same idea, radiates, it could be a radii. Everything's kind of got the same proportion. The takeaway is this, that we did like a little bit of an exploration in class. We can do a quick look at it. I don't think it doesn't take that long. Let's say I had a rectangle here with side lengths 3 and 1. And let's say I had a similar rectangle here, but not, this side length was 9 and this side length was 3. So everything, hopefully really easy to tell from left to right, is 3 times bigger, right? Okay, so there would be a scale factor from left to right of 3 to 9, which, or if I reduce it, it's the same number as 1 to 3. Okay, or if you're going right to left, you'd say there's a 3 to 1 scale factor. What's the area ratio? Is it 3 to 1? Let's see, what's the area of this figure? The area is base times width, or length times width. 3 times 1 is 3. What's the area of this figure? Area of 9 times 3 is 27. 9 times 3 is 27. Well, that is definitely not 3 times bigger, right? So if I'm kind of comparing areas, this 27 is actually 9 times bigger. So that's where, and we've talked about this in the past, that there's a different ratio for areas. The area ratio has a 1/3 squared ratio, so a 1 to 9 ratio. Okay, in this example, the area is 9 times bigger, not 3 times bigger. One last look. What if we throw now? Here's kind of the new part. What if we throw? Let's see if I can do this without making it too disastrous here. That like a third dimension, and say we went back 2 units. There's a depth here of 2, so we could crunch. Hey, the lengths, everything was 3 times bigger. So if this is 2, this would have to be 6, right? 3 times bigger. But now if I say, hey, what's the volume of this? And what's the volume of this? Let's see what happens. So volume would be area of the base, 3 times 1. What do we got here? Oh, no, the area of the base would be 3 times 2, and then the height was 1. So 3 times 2 is 6. So my volume ends up being 6 here. What's the volume over here? 9 times 6, which is 54. Okay, the area of the base. And then times the 3, though, our volume is 162. Is that 3 times bigger? Well, that's way more than 3 times bigger. Is it 9 times bigger? Well, 9 times 6 is 54. There's a third dimension here to it. The volume ratio is 1/3 cubed. So 1 to the 3rd power, 3 to the 3rd power. There's a 1 to 27 ratio amongst the volumes here. So I took 3 to the 3rd power. That's where the 27 comes from. I guarantee that if you check, 162 divided by 6 is 27. This number right here is 27 times bigger than this. So that's the note. It says it right here, that if 2 similar solids have a scale factor of k, then the ratio of their volumes is equal to k cubed, or to the 3rd power. Okay, so that's kind of the big reveal, or the big, at least I think that illustrates it okay, as far as seeing it there, that depending on what kind of unit you're talking about, are you talking about length, are you talking about area, are you talking about volume, you have 3 different ratios. Okay, so let's look at an example. I think this is a pretty typical example from this type of section. See what we do with it, okay? All right, example 4, pyramid A, pyramid B are similar, so it tells us they're similar. That's like, we kind of need some of that information. asking us a couple things. Find the ratio of the volumes from left to right, from pyramid A to pyramid B. Okay, so it should be like a bigger number to a smaller number. And then use that volume ratio to find this one's volume. Okay, so formulas are kind of off the table. We could kind of reverse engineer this here, but let's use the ratio in kind of a more typical way, because there are going to be cases where there's just the formulas don't even apply. Like we have to kind of do it this way with the ratio. Okay, so they all kind of start the same way. That I still have to identify that scale factor, the length ratio. So I can see that there's an 8:6 left to right ratio on the heights of these pyramids. Okay, 8 meters to 6 meters. So we should reduce that, just like we did on our little mini example before. There's a 4:3 left to right scale factor ratio. Okay, now that's great. That's awesome. We could use that if I needed to find, like side lengths down here, or maybe one of these edge lengths, something like that. There would still be a 4:3 ratio. But I can't use this to find volume. I need to, what did we just say? Cube, take to the third power this 4/3. Okay. So this 4/3, if I take that to the third power, that means 4 times 4 times 4, which is 64. And I need to take 3 to the third power as well, which 3 times 3 times 3 is 27. So there's not a 4:3 ratio on the volume. My K cubed, or my volume ratio, is 64 to 27. These are not the same number. 4/3 and 64/27. I know they kind of look like, oh, doesn't this reduce to this? But they're different. This is a lot bigger. I mean, relatively bigger. If you were hungry and said you can have 4/3 of a pizza, although that doesn't make a ton of sense, or 64/27, you'd rather have this. This is 2 whole pizzas, versus this is just slightly over 1 and a third. Anyways, there's my volume ratio. The last part is, okay, then it says to use that. So use this 64/27 to help us find this one's volume. Okay, so if I kind of follow that left to right setup, I kind of went left figure over right figure, left figure over right figure. I got to come back and say, all right, I know the left one's volume is 96. What is the smaller one's volume? So that 96 has got to go in the right spot, because obviously when we cross, how are we going to solve this? I just gave it away. We're going to cross multiply. 64V equals, let's see, 27. Got to go for the calculator. 27 times 96, 2592. And then divide everything by 64. Now, the good news is we're good at this. We've cross multiplied all semester. It doesn't always work out to be exact, but I guess you have a greater likelihood of it being exact. That, hey, 40.5 cubic meters is the volume of this smaller pyramid. So just to finish the thought there, they don't always work out to be exact, but like I said, there's a little bit maybe better of a chance, because you're not, there's no trigonometry, there's no pi involved, but it still could be a decimal number. So that's it. That's what we got. I think it looks okay. I just want to make sure we're still recording there. Yeah, let's check it out. I mean, I think we hit them all. It was using those formulas. We did throw on, I should maybe have a second point here, of using similar solids, but we got it all done. We're okay. So do the best you can with the homework. We'll call it there, and I'll see you in future lessons.